Thus far in our discussion on benzene, we examined the electrophilic substitution reactions in which the benzene molecule acts as the Lewis base, the nucleophile, and the electrophile acts as the Lewis acid. But do we have reactions where benzene acts as the Lewis acid and the other molecule acts as the nucleophile, the Lewis base? That is, do we get a reaction when we take benzene and mix it in the presence of a strong nucleophile? So it turns out that any unsubstituted benzene will not react with the strong nucleophile, so no reaction will take place between the benzene and a strong nucleophile. However, if we take this benzene and we substitute that benzene with some type of group, electron withdrawing group, in a special manner, we will produce a product. So one particular example is the following reaction in which this polysubstituted benzene ring reacts with a strong nucleophile, the methoxy group, and this produces our product. So we basically replace this chloride atom with this methoxy group. Now the question is, why is there a difference? Why is it that this reaction does not take place, but this reaction does take place? And as always, to actually answer this type of question, we have to examine the mechanism of this reaction as well as the intermediates that are formed. Now the question is, what is the reaction by which this pathway is followed? How exactly does our nucleophile attack our benzene ring, displacing and replacing this chloride atom? So let's begin by asking ourselves, can an SN2 reaction take place? Well, for an SN2 reaction to actually take place, there has to be space on that carbon because our nucleophile must attack from the back end of that carbon. But the back end of this carbon is sterically hindered by all these other atoms. And so an SN2 reaction will not be able to take place because the methoxy group will not have enough space to basically attack the carbon from the rear end. What about the SN1 reaction? Will an SN1 reaction take place? Well, the first step of the SN1 reaction is for our leaving group to basically kick off, to detach itself. But this only happens if the bond that holds the leaving group, the chloride, to our carbon is a weak bond. But in this case, the carbon-chloride bond, in the way that we showed here, is not a weak bond. So the chloride will not simply detach itself from our carbon-containing benzene molecule. So what other type of mechanism is possible? Well, it turns out that the first step of this reaction basically involves the nucleophile simply attaching itself to this carbon that contains our chloride. And it kicks off this pi bond, placing those two electrons onto this carbon here. So basically we have two electrons on this carbon, and that means the carbon has a negative charge. Now this negative charge will be delocalized. It will be spread out to 3 different carbons. So if these two electrons form a pi bond here, these two electrons will be kicked off onto this carbon, placing a negative charge onto this carbon. And if these electrons conveniently decide to form a pi bond here, then this pi bond will be kicked off and those two electrons will be placed onto this carbon, placing that negative charge onto this third carbon. So the negative charge basically resonates between these 3 positions. And notice that in this particular case, we form a carboanion. Our carbons have a negative charge. In the electrophilic substitution case, when our benzene acts as the nucleophile reacting with the electrophile, we form a carbocation. But in this case, when the benzene acts as the Lewis acid and this acts as our nucleophile, the Lewis base. We form a carboanion intermediate, and we only form this when we have this type of resonance stabilization. Now, notice what other effect is playing a role in stabilizing this intermediate. So it has to do with the fact that we have these two electron withdrawing groups. So basically these two NO2 groups contain electron withdrawing atoms, namely the nitrogen atom. Now nitrogen has a greater electronegativity, a greater attraction for electrons than does carbon. And that means when the negative charge appears on this carbon and when the negative charge appears on this carbon, because there is a nitrogen atom attached directly to these carbons, that nitrogen atom will basically pull some of that electron density away from the carbon, which is the less electronegative atom. And so we have a buildup of electron density here, but this nitrogen will basically pull some of that electron density away from here and from here, and that will stabilize this molecule by decreasing the electron density found within this ring. Once again, this first step basically forms a resonance stabilized intermediate carboanion that contains a negative charge. This negative charge is spread out among 3 carbons as shown, and 2 of these structures contain carbons that are located right next to the electron withdrawing nitrogen atoms, and these nitrogen atoms will play a role to stabilize the intermediate by pulling away some of that electron density from these carbon atoms, and that will stabilize this intermediate. If we compare this reaction in which the nucleophile attacks our benzene ring, the benzene ring does not have any electron withdrawing atoms as it does in this case, and so it will not have that very stabilizing effect. And that's exactly why this simple reaction with unsubstituted benzene and the strong nucleophile does not take place, while this reaction does take place. So excuse me.